Thank you for having me here this afternoon. And I'm very happy to present two of our ongoing projects at the Operating Systems Group at HPI in Potsdam. And both are centered around making FPGA accelerators a more accessible topic for, well, let's say software engineers, because at HPI we are predominantly software engineers. So I don't think that I need to introduce the benefits of using FPGA accelerators to this group, but perhaps to highlight one particular advantage that is important to us, at least, is energy efficiency. As FPGAs are able to operate at lower clock frequencies, which are perhaps sufficient, at least for a very large variety of application scenarios, they usually do need only a fraction of the power an equivalent CPU or GPU would use. And that means that if we are able to port some kind of algorithm to an FPGA, we are likely to encounter a much better performance per watt ratio. And this is very interesting because at our group we are researching into the question of energy-aware computing, energy-efficient computing, and all this kind of making your data center operate at more efficient power consumptions. One usual stumbling block from a software developer's point of view when targeting FPGAs is, of course, that they need an entirely new mindset in contrast to software development, because at least if you are operating on the lowest level, the HDL or hardware description level, then you are faced with inherent parallelism, which contrasts to the inherently sequential nature of most programming languages. You are also faced with a problem that you cannot simply call subroutines or something, because this kind of thing on an FPGA level usually behaves like an inline function. If you call a function multiple times, or you, in the right language, instantiate it, you are faced with a very large design for perhaps no great utilization of your hardware. And also, if you haven't done any kind of basic hardware architecture course during your university training, it is perhaps very difficult to, well, define your microarchitecture efficiently. And all those problems come on top of, well, perhaps the not that far advanced ecosystem of tool chains and development methods for hardware development, because most of those tool chains are still very proprietary and not very flexible in terms of using different development methodologies. So it's difficult to get into, and therefore we have been working during the past 2 or 3 years on two projects. The first one that some of you who have been here last year might recognize is MetalFS, and the other one is de facto. Having the same goal, they are very different in the level of abstraction at which they operate, so perhaps we are able to draw some nice comparisons here. First, coming to MetalFS. The basic idea is focusing on near data computing, and actually because we have an FPGA card that features 2 terabytes of NVMe storage, which makes it very interesting to explore these kind of workloads. And well, as you might imagine, we just have an FPGA on the path between the CPU, which communicates with the FPGA via copy 1 in this case, because it's quite an old card. And on the other side, we have just the FPGA communicating with the NVMe storage blocks. And to make this these resources on the card available, we, on the one hand, provide an FPGA overlay, which is just some kind of template architecture where you can define your functionality in a very fixed framework that allows you to avoid re-implementing all those kinds of usual operations like fetching your data and having to determine where you want to put it and so on. So you just focus on the computation part. And this is the role of operators. So an operator is some kind of piece of hardware that is closed in itself and takes one incoming data stream and produces one outgoing data stream. It is possible to do to define more complex things, but we will come to this point perhaps when we are talking about the de facto framework. And to have some kind of runtime flexibility, we added a crossbar switch that allows us to combine these operators freely at runtime, so data can flow through whatever setup a user wants to have. As I already said, the project lives inside the copy environment and uses the Snap framework for its basic infrastructure, like accessing memory and the NVMe storage and whatever. Okay, so here is one way, which perhaps might not seem obvious, where we are accessing our FPGA accelerator card using basic shell syntax and using basic shell syntax. The thing here is that we are running binaries and taking data from this mount point called MFS, which stands for MetalFS, and this is the place where the MetalFS software layer mounts itself actually as a user space file system and exposes everything that is built into the FPGA design and everything that is available on the NVMe storage blocks to your basic environment, where you can use it as a simple non-root user. And as you see, if these operations that are exposed in the operators section are called, they actually do not cause data to be routed to the CPU or RAM on the host system, but are translated to equivalent configurations for the FPGA on the card. And also, the data stream from the NVMe storage is routed directly to the FPGA, so that only this last pipe here corresponds to data being moved on the host system. And in this case, we also add some kind of host-side processing to highlight that those things are interoperable. And in the end, we store the result of our operation on the file on the host system, which might be attached here on some kind of spinning disk or SSD or whatever. Right. To make this possible, we have this one central process that manages this fuse mount point. And this one has quite a variety of tasks. On the one hand, it is the primary owner, so to speak, of the FPGA card. So it holds the handle to all the snap and whatever copy context and controls the card via that path. But it also stores the file system metadata. So this SSD is the place where you store the data of your files that are here, but the structure, so the file name file.bin and its access permissions are actually stored on the host system because it is not efficient to handle this kind of dynamic metadata stuff on the FPGA card, because there it's only interesting to get the raw data streams. And yeah, there are some more, I think, tricks to be able to have these pipe constructions map their operations transparently to the FPGA card without having to route a data stream from the FPGA card to the host and back to the FPGA card. So there's a story behind it, but I think it's not that relevant here in this place. Right. Having this high-level interface, which might be sufficient for many users, it is also necessary to, well, have a decoupled lower layer where you can write your own applications in C++ against a well-defined API. And we are going to look into this part also. So here we can see a high-level view of one possible FPGA design that you built with MetalFS. All the lighter gray components are actually user-defined, so they are not they are perhaps provided as an example with our code, but it's not necessary to use them. And all those on the blacker ones are what is predefined from the FPGA overlay. Central part is here the stream switch, which connects all operators that are present. And those two blocks act as operators, but are actually interface blocks to main memory of the host system or NVMe storage or whatever other resources are on the card. And if we go through this, we see that with the C++ API, we are able to query the design, which operators are present on it. This configuration is actually stored in the FPGA card in a separate configuration memory, so it is possible to, well, take out your card, go to another machine with MetalFS present, and it will be able to just query which operators are present and then present them to the user. And in this case, we query an operator called encrypt. And we also have to set which key should be used to encrypt it. This key buffer is just some kind of memory buffer in host memory, which is accessible to this operator because it can just go to through the OpenCAPI link. During, while this pipeline we are going to construct is not operating, this OpenCAPI link is actually accessible to all those components for the configuration phase. So this encrypt operator can just query the buffer and host memory and load the key in its internal state. So having added the key, we have to configure our data source and sink. For a host memory data source, we just pass a pointer because both the card and host memory are in the same virtual address space, so we can just pass pointers. On the other hand, interacting with the NVMe storage requires us to present an extent list, which would be generated by some kind of host-side metadata storage component. And finally, we have everything set up. And this statement here causes the stream switch to be configured in a way that all those unused stream links are just down, and only the active ones are used to convey data. And running the pipeline causes the actual data to flow, and then we are off. Right. We have prepared a small demo to see perhaps more of the one moment. To see more of the development perspective using MetalFS. Is it communicating with me? I hope so. Right. At first, we are going to clone the software from GitHub, and then we are moving in some predefined code. We will look into that later. In this repository, there is already a space called example, which has all the infrastructure you need to start designing your own MetalFS image. And we are going to look into this environment. And there we see that already the change, this change case example operator is present due to which is predefined everywhere. And this filter directory we just copied from our demo environment. There's also this image JSON, which is some kind of manifest that tells how the image on the card should look like, and some other stuff which is not that important. Looking into the image JSON file, we see there is some kind of predefined situation where you have many operators. Some of them are loaded from sources on the internet. But for our use case, we just want the filter operator. And another interesting thing is we can define in this file which byte count we want for our interfaces. In this case, we have a 64-bit data stream connecting data sources and operators together. But as we are doing some very simple operation that can do with a little more parallelism, we change this to 64. So in terms of CAPI1, this consumes the whole 512-bit of available through the CAPI interface. And looking into this filter operator, we see that the value we just set is available as an environment variable for us to determine how we want to build our operator. You do not need to think about the specifics of this code, but it is important that you are able to write data stream with independent operators using those environment variables. We see here an example where we check how many values of 64 bits will be in our data stream, and then choose different implementations that are more efficient if they do not need to handle more than one value per stream element. We also are able to have a manifest for each operator, and in this case we use it to give it two command line options. This file controls how in this user space file system you would see the operator, and causes two options called lower bound and upper bound to be available with the host side interface. The whole development process is Dockerized, so we can roll it out on most platforms that we are working with. And right, you see, at first we are building the software side of MetalFS, which is not that interesting. And now we are able, in this specific environment we have for defining images. You can use any other folder, but then you have to set up the directory structure properly. So we just use what is predefined. We enter this, and there is a makefile that encapsulates the entire process, build process for our code, as well as the snap and copy whatever layers. So this takes quite a long time. Not in this case, but it took quite a long time, about 4 minutes. And now we can just run the simulation and find, after the simulator has come up, this command exchange here actually marks where the host system queries which operators are present on the FPGA card. So this data buffer there is just some condensed kind of this manifest we saw earlier, handed back to the host software. And now we can see that in this, this is just the preparation of our test file. And now entering the same Docker container, we see that MetalFS is present in its mount point, and that the filter operator is listed under the operators section in this mount point. So now we are able to pass this test file, where we see there are only 4 different kinds of values, 1 to 4, through the filter operator, limiting values to 2 and 3. We see on the simulator side that actually the FPGA hardware is, simulated FPGA hardware is doing something. And now it's ready, and we can examine the output file and see, whoa, less values and only 2s and 3s, so it works. Great. Second. Okay, just a short recap of what we are doing with MetalFS. This is some kind of canonical way of describing the development flow for hardware development, with a special focus to the Xilinx Vivado toolchain. In this backend, we are doing all this processing of hardware description sources to some kind of representation for either simulation or as an image on the FPGA. And in this front end here, we have multiple ways Vivado presents us to to work on a higher level of abstraction. And custom operators with MetalFS will usually be implemented in HLS because it's very fine to represent stream operations. The hardware side of MetalFS is implemented as a block design because that was the easiest way of defining that structure. And the whole rest, the rest of the demo you saw was this more integrated MetalFS build process, which handles all this part for us. Coming to the de facto framework, we see that it operates on a much lower level and harks back to this aspect of, well, letting Xilinx give us a way to express some kind of structural high-level design or more of a procedural high-level design, which are very powerful tools when used rightly, but have this limitation that they are rather vendor-dependent and, well, have, to my mind, are sometimes a little opinionated about how you should structure your workflow, which did not fit well with our work, so we were thinking about different ways of doing it. And our approach here was to, instead of having block designs, using an instantiation language that provides the same level of abstraction, but is not a graphical format, but a text format, and also to let it produce synthesizable VHDL, so it does not require us to use the entire Vivado toolchain afterwards. We just can take this synthesizable VHDL to any other platform we want. This is one half of the picture. And the other one is having a library of predefined open source components, which encapsulate much of the commonly used blocks when using data stream operations. So we will see an example shortly where these come into play. The very important part was that we wanted, well, this is some kind of contrast to what is usually found in the Vivado IP catalog. These components are usually defined to be very powerful and complex and have many different application scenarios. And we wanted to do just the opposite, having each component do exactly one thing, and that only at the most rudimentary level, and then have a system of composable modules that come together to perhaps create the same effect, but do not need to create the whole feature set that the IP component would have done. So as an example, we want to focus on the table scan accelerator. So we are imagining that on our host system, we have a database management system that has stored some tables on the storage resources of our accelerator card, which features, as I already said, the FPGA and some storage. On the storage, we further assume that it is a column-oriented format. So you see all the values of one column in one contiguous space of memory, and then you see the next column at a different address. So you can actually see each of those columns as a stream of data, which is very important for our design in the FPGA. And we want the FPGA to perform some kind of equivalent operation to this SQL query, like filtering on one or more different columns and just returning us the rows that we are requesting. So a very simple use case, not tailored to any specific platform, just to have an example that seems at least realistic. Right. The design that we, well, came up with for this, it's just an instance. You can design anything you want, but in this case, we are limiting ourselves to at most 4 columns per query. We can do different trade-offs, but for this use case, we just chose it. And those columns appear in 2 different places in the query, so they also have 2 different paths to travel through our accelerator. Appearing on the output side of the query, we have these straight paths going to the result columns. They pass through selectors, which just either pass on a stream element or discard it. And the more interesting part is this part below, where the comparison and conditional logic lives, where we can route any 2 columns to any comparator. Each comparator produces a stream of Boolean values, and to allow us some kind of arbitrary Boolean function between different comparisons, we have a conditional logic block that combines 4 Boolean values to 1, and these are routed to the selector nodes. Unfortunately, we cannot keep it that simple if we want to realize this design, because we have to somehow get hold of the data streams, somehow make sure that the data streams flow freely and do not block up or something. So in this case, we can rely on some of the predefined components from the de facto framework. The more important ones are those DMA components that take a standard XE interface and convert it to an XE stream interface. So we are able to configure those with an address range, and these just load the data and stream it on. Furthermore, we have those 2 switch or router components, which are just crossbar switches that can be configured at runtime to realize different comparison scenarios. And we are using those stream buffers. They are important because, as you see, the pipeline length of this half of the design is not the same as this half. And as those streams are synchronous, we would actually block up the entire design while data or comparisons are performed here. Because those stream splitter blocks require us to process, require both output streams to process the data or accept the data until they allow the next item to be presented. So in this case, the selector would need to wait for the corresponding Boolean value of taking the row or not taking the row, while and would hold this data stream in some kind of wait state until it has this information. And the latency of this pipeline would actually limit the bandwidth of the entire design, and this is not desirable. So we need a stream buffer that is exactly as long or longer than the latency of this pipeline here. So, but one a positive point is that we can use predefined components for that. We just need to keep in mind what their semantics are. And the only thing that the user would need to build are those 4 logic blocks. And as these are stream processing operations, they are, as I said already, very nice to define in HLS. So we are just having a look at this condition logic block, which takes an arbitrary logical function and transforms and applies it to 4 separate Boolean values. And we see the equivalent HLS code for the entire condition logic block, and it's not that bad. Other ones like the selector and everything else are on the same level of complexity, perhaps longer, perhaps shorter, but not too difficult to build. And finally, we have to put everything together. And there we come to our instantiation language approach. It is a very thin DSL layer built on top of Python. Actually, it's just exporting some special symbols like this instance and entity and sequence statement into a Python environment. So it gives us the power of a script language to define which and how we want to instantiate blocks. And also, it allows us to have a more concise format of describing the structure. So you can compare this section of our design. It is described completely by those by those lines of instantiation script. So in this loop, we instantiate the 2 condition logic blocks, and the stream router comes after it. And connections are just identified by unique signal names. So this stream log 1 and 2 are going to this stream log 1 and 2 and are automatically connected. And this smaller example now is getting compiled through our template mechanism into this block of VHDL code. So you see, much is missing from this, but just to have the equivalent of this shorter segment, we have here the instantiation of the master stream router entity, and underneath some kind of vector unpacking, because we have here a list of signals that are connected to a single port, so we have to unpack them manually, which would be quite tedious doing it manually in VHDL, but we are happy to have this kind of more concise form. As you perhaps note, it's difficult to read. The names of the signals are actually preserved in the generated VHDL, which gives us at least some measure of traceability, which we found very important to debug whatever design is coming from it. Right. So here we have some kind of overview of what we have been doing with our framework. All those parts here we know already from the traditional hardware development workflow. So that was also an important point for us to ensure that all kinds of design processes which are already present should be interoperable with whatever we are doing with our framework. So the only requirement here to include some module built by the user is that it must be instantiable from a piece of VHDL code, and most processes either generate VHDL models themselves or export it in some kind of format that the IDE of the Vivado IDE can parse and use to build hardware from them. Of course, if you use block designs or HLS sources, you lose the portability of your design. But on the other hand, if you stick to only HDL sources, then you are able to combine it with any toolchain you want. The de facto part has its root in this script, this instantiation script that shows how the top-level design should look like, and also in this library of predefined components that allow us to have some shortcuts in our design process. From this, we generate via template expansion simple VHDL code, and from there on, we just follow the regular development process as we've seen already. So this is a very lean addition. It actually fits inside a copy snap action without too many tinkering about, but we will see when we integrate it how that works. Right. Coming to some numbers. One thing that was also important to us was that any component that we build should not itself introduce a bottleneck into the path that it is put in, because if you have some kind of abstraction and you suffer from it, then you won't use it. So those components are only useful if they do not themselves impose a bottleneck on the design you're building. So we did some tests with these DMA modules, at least. We also took the other modules through the same thing, but I don't want to overwhelm you with numbers. And we see here the situation that those components are reading a consecutive buffer of memory of varying sizes, or in this case, write this consecutive buffer of memory, and have a trace which kind of clock cycles were passed during that time. So we have active cycles. These are clock cycles where actually a piece of data is moved from one place to another. So when this data stream shifts one piece of data out. There are latency cycles which are specific to the AXI interface, because this is the time from issuing an address request or a read or write request with an address to the first time the data was accepted, or at least in the read case was presented on the corresponding channel. So this latency decreases with block size because we can better utilize the request pipelining options from the AXI interface. So this is also expected. And the other part of the cycles are either master or slave stalls. Stall mean that either party is able to accept or produce or send data, but the other party in the communication is not able to receive it or produce more data. And the master side is associated with the outgoing or incoming data stream on the AXI stream interface, and the slave is the kind of memory controller component that is attached via the AXI interface. And as we see, there is no kind of master stall introduced by our components. The only bandwidth limitation comes from the slave, which is not able to produce or accept data at that rate that we were trying to achieve here. This is a copy1 interface. We also did some measurements on the copy2 interface. There, the proportion between slave stall and active cycles is, of course, a little more favorable. Right. The other aspect is not performance, but FPGA resource utilization, because there's this second path of not using a provided abstraction because it is too large to fit on your FPGA together with the design you already built. And there we also have some comparisons, at least. For the DMR reader or writer, which are associated with AXI reader and AXI writer, we just chose a more general term because we had to find some kind of equivalence. They do not use that much that much space on the FPGA, which is, of course, expected because they do the absolute minimum of what they need to do and omit some kind of feature that would have to be introduced on the path, perhaps by combining them with an additional stream buffer or any other component that is provided with them. But the components themselves do not use too many resources. Also, the stream switch, which is or router, as we have seen, which is an important component, is not too expensive. And the absolute minimum which is required with our framework is this de facto core part, and that also is not too much an overhead to pay for using this level of abstraction. You can see here a floor plan of rudimentary design just using those components on the FPGA. All those gray parts are infrastructure either from CAPI itself, this darker gray, or from CAPI Snap, which provides the memory controllers and NVMe controllers and whatever we need. And the actual components that we added to this are, well, small enough to fit in. On the other side, we see the MetalFS overlay, also configured to have no operators at all, just having the infrastructure. And we can see that there we have a much larger footprint, which is due to the fact that MetalFS just uses the basic IP components from the IP catalog, which, as I said, are engineered to be much more rich in features and more generally usable. So they are, as we can expect, much larger, but also have a larger feature set. So we can see that de facto at least provides a new point on this continuum of trade-offs that you can choose between flexibility and resource efficiency, so to speak. Right. I think that's it. Just, well, to conclude, we have two ongoing projects that attempt to introduce some more convenient level of abstraction in this whole process of developing FPGA accelerator applications. And yeah, I think there's much work to be done, but yeah, at least it's a good direction. In this sense, I also want to thank everyone who worked with us, especially people from the IBM labs in Böblingen and Montpellier, who, well, besides giving us valuable feedback, were often involved in extensive debugging sessions. So thank you very much for this. And yeah, with this, I thank you for your attention. And if there are questions, I'd be more than happy to answer them. Mm-hmm.
But I couldn't see, is there any comparison between the FPGA and CPU version? Which were faster?
I think there's a misunderstanding. We are here just talking about the raw performance metrics of those components which we built. The design we have outlined before is just an instance of what you can build with it, but the measurements we present here are for the components themselves. So without any them being introduced in some kind of infrastructure.
Okay. So this means you are only evaluating the performance of the component.
Yeah. So it was important for us to see that they do not impose a bottleneck, because whichever design you build, it's very specific to the design you have built. So if we just choose one example design where everything works fine, it's not a good way to express the efficiency of our framework. It could just be a good design. So that was the rationale behind that.
So have you ever tried to integrate this component to a real database?
Not yet. As I said, it was only a concept which was used as a realistic example. But well, we do not think that it is out of the question to do it if there should arise some kind of cooperation with the other group working at HPI that focuses more on databases themselves. Hmm? Yeah. Yes. Second, there are the links. We are hoping to integrate it into the Snap framework as an example action, but this is still in progress, so it would be best to just use my fork of the Snap repository, and there you find it in the outdated name POSIX branch, where it is placed as a separate action, and yeah. Mm-hmm.
Similar to what and compared it to a filter so that it's just the same CPU. So the difference is regarding the selectivity, right? So if you filter for a range of numbers and on the CPU the runtime depends heavily on how many values you have in your index. Right? So if you filter 50% with the branch predictor will have a hard time. All is static, independent of how much revenue you give all this.
So on the bottom line, we just had this situation where with about 50% selectivity, the FPGA outperformed the CPU, but at 0 or 100% selectivity, obviously the CPU was faster because it has this faster link. So we did this on CAPI 1. I don't know how it would perform on CAPI 2 or later.
Modern databases is very efficient for CPU version. So we are struggling on constructing a FPGA version to compete with the CPU, especially when you can fully utilize the multi-threading CPU and multi-process. So FPGA, if you compare your FPGA with 1 or 8 or 16 threads of CPU, it's okay, but CPU usually can use more than 100 threads running around. So it's a big problem for us. We are struggling on that. So that's what I asked.
So the bandwidth from the NVMe to the processor is small. So the huge memory bandwidth is not that important for the CPU. So the FPGA can be very efficient in that explicitly because you cannot utilize the bandwidth.
That's good.
Further questions? Great. Then thank you again, and